Hello, everyone. Welcome to the second workshop of this ICP Chain Fusion Educate Bitcoin edition. I'm going to wait for a couple of seconds for people to arrive. Hello in the chat. Today we're going to be, workshop is going to be led by the lovely Moritz Fuller from DFINITY Foundation. I'm going to invite him on to the stage now.
What's up, everyone?
Hello.
You see one familiar face in the audience, which is great.
Yeah.
And you, of course.
Great. Maybe we can wait a little bit longer for people to arrive and then we can start.
Yeah, a lot of ground to cover today. This one's going to be a long one. So I think we, depending on how strict we are with the time today, we might only have like 5 minutes left for Q&As. But if you have any particular questions, you can DM me on Twitter or on our forum or whatever you prefer. I basically have the same handle everywhere. So I go by Crypto Schindler on all major social media platforms. So if anything is left unclear at the end, please feel free to reach out. All right, so Chain Fusion, again. We had a previous Educate series that also covered Chain Fusion. But the last time we focused a bit more on Ethereum, and this time we focus a bit more on Bitcoin. So this presentation is called Chain Fusion Bitcoin Edition. And a little bit about myself. My name is Moritz. I'm a senior developer relations engineer at DFINITY. I've been in the ICP ecosystem for more than 6 years now already, so quite a long time. And yeah, today I'm talking a little bit about Bitcoin and what you can do on the internet computer with Bitcoin. And throughout the slides, there are a number of QR codes in the top right corner, and you can scan them if you keep your phone out. But luckily, on the next slide, on this one, there's a single QR code, and that should be sufficient to scan because this one will get you to the presentation. And if you have the presentation, you can just click on the QR codes. And the QR codes basically get you to further reading material or to more information about the topic that is covered on the slides. And so I assume most of you already know what the IC is. So I'm giving a very, very brief intro on it. So in one sentence, the internet computer is a decentralized and permissionless cloud built on blockchain technology. And here you see the topology of the internet computer. So at the bottom, those black cubes, they are data centers, and node providers run nodes in those data centers. And the nodes then again form the things up here, which are subnets. So every subnet is basically a small independent blockchain, and every node, like those gray rectangles down here, can only be part of one subnet. And as you can see in this picture already, the internet computer doesn't consist of one subnet, but actually of many, many subnets. And all those subnets run in parallel. And to give you quick rundown on what that is. A subnet is basically a replicated state machine. And that means that each node within the subnet performs the same computation on the same state. And something special or cool about subnets is that they can seamlessly communicate with each other. So that, of course, in turn means that if you have a smart contract or a canister, how we call them, deployed on one subnet, basically the one on the left here, for example, that you are able to seamlessly communicate with canisters deployed on other subnets without having to jump through any hoops. And this is a feature that allows the internet computer to scale horizontally. So if the internet computer would need more computation or storage, for example, what it would do is that it would basically just spin up a new subnet with new nodes, and that's it. And I quickly want to talk about canisters. So canisters are basically an evolution of smart contracts, as you might know them. And I think it's easier to think about them as decentralized servers than traditional smart contracts because they share a lot of common things with a decentralized server, not so many things with a smart contract, except that they are running on a blockchain. And there are a number of very good features. I'm just going to talk about the 3 features that we care about today. But if you want to find out more, feel free to scan the QR code or click on the QR code in the top right corner. So the first feature I want to talk about are HTTP outcalls. So HTTP outcalls allow canisters on the internet computer to call into Web 2 services, like, for example, an exchange rate API or an RPC provider. And that is without any additional infrastructure needed. So you as a developer, you can just use this feature out of the box. Usually you would probably rely on some sort of Oracle infrastructure for that, and you would need to pay for that. But on the internet computer, if you use a canister, this comes included. Then the next thing I want to talk about quickly, and that we are going to cover in more depth later on, are chain key signatures. So thanks to chain key signatures, a canister has control over unique ECDSA and Schnorr key pairs, and a canister can also request signatures with the corresponding private key to be computed. And this enables canisters on the internet computer to natively hold, for example, Bitcoin, Solana, or Ethereum, and many, many other chains or tokens from other chains, because those chains all support the 2 signature schemes that I just mentioned. So ECDSA and Schnorr signatures. If you have those 2, you basically are able to hold funds on any major layer 1 or blockchain that is out there. And the last feature I quickly want to cover is the fact that canisters on the internet computer, they have a very, very big amount of storage available. So on the internet computer, on a single canister, you can store currently up to 400 gigabytes with plans to enable terabytes in the future. And that's pretty cool because a single gigabyte being stored on a year on the internet computer only costs you $5, while the same on Ethereum, I think, I don't have this in this slide deck, but I think it was like 18 million or something, so an absurd amount of money. And on the IC, you cannot only do computation, but you can actually also store data, which is very neat. So chain fusion, you might have heard this term already. We kind of use it as a very broad term. It's like an umbrella word to describe many things in our ecosystem that are all aimed to basically fuse the internet computer together with other chains. And the overall idea of chain fusion is to be able to leverage the properties of multiple chains within a single dApp. So we want to bring the internet computer's strength to other chains, and of course, vice versa, the strength of other chains to the internet computer. And chains that we currently kind of like directly support with chain fusion are Bitcoin, and this is what we are talking about today. Then also Ethereum, most EVMs and EVM-based L2s, and upcoming, we will probably also support Solana. And in today's talk, we're going to focus on the areas that you see circled red here, so chain key signatures, in particular on CK, chain key ECDSA, and chain key Schnorr signatures. Then we're going to focus on the Bitcoin direct integration, and we're going to talk a little bit about the Bitcoin adapter that enables this direct integration, also on the Bitcoin canister. And then we're also going to talk about chain key tokens, and in this case, we're going to focus on ckBTC, so chain key Bitcoin. Maybe as of now, you already ask yourself, okay, yeah, chain fusion, I don't know, fuse together different chains. What does this do? What can I do with that? And that's why we have this slide with give you a bit of an idea what's possible with this. So for example, you could use Bitcoins or any other L1's liquidity that supports the signature schemes that we mentioned earlier in cross-chain smart contracts. What you could also do is that you could split your logic of your application and the storage between the internet computer and another network. For example, you could store data on the internet computer because it's very cheap, and you could do settlement if you want like a lot of security on Ethereum. There's also a pretty strong and very versatile use case that is using the internet computer as a co-processor for Ethereum and other EVM chains. So the idea here is that you take computationally intense tasks and you run them on the Internet computer, and then you take the result and you write that result back to the source chain. So for example, on Ethereum, the amount of computation that you can do within a single block is, for example, not enough to calculate, I think, the 20th Fibonacci number. But you can do that on the Internet computer. So an Ethereum smart contract could say, hey, please calculate this for me. And if you got the result, please write it back. And all of this is possible in a trustless way, right? There's no intermediary or no additional infrastructure needed. It's just the Internet computer and the Ethereum network. And that's it. That's pretty cool. One use case here is, for example, the on-chain generation and the on-chain storage of dynamic NFT metadata and dynamic NFT assets on the Internet computer, while the ERC20 smart contract, so that basically the NFT ledger, lives on Ethereum. And that is, if you, on the Ethereum network, mint an NFT, that NFT is literally created. So the JPEG is computed on the Internet computer and stored on the Internet computer and generated on the Internet computer along with the metadata of the NFT. And that's like one use case I find pretty intriguing and very, very cool and nice to visualize also. And then you can have multi-chain smart contract wallets. So you have a smart contract on the Internet computer that has access to those ECDSA and Schnorr signature schemes. And that means that this Canister is able to hold funds from many different chains. And the cool thing here is that you do not need to basically have like let's say like a key pair that you somehow need to manage. Like you don't need to write down a seed phrase or something, but you could authenticate to the smart contract wallet, for example, with your cell phone using passkeys or any other a bit more user-friendly way. And then you could also control any smart contract on chains that support ECDSA signatures from an Internet computer smart contract. And you could also do this the other way around. So you could basically let smart contracts on other chains call into or kind of like control smart contracts or canisters on the Internet computer. So as you can see, some of those things are pretty fundamental, and you can do many, many things with them. And it's basically up on us, up on the developers to come up with cool new ideas and implement them. And I think it's nice because there's a lot of uncovered and unknown grounds. So a lot of untapped potential, in my opinion, that can be brought up with this kind of technology. Okay, so in general, how does this work, this chain fusion? So in general, you always need two key building blocks. And the first one is that you somehow need to securely read from and write to the chain of interest. And the other one is that you need to be able to sign transactions for the other chain of interest. And for the left-hand side, there are two different approaches. The first approach is this direct integration that we have with Bitcoin. So here we basically verify the consensus on the other network in the Internet computer. And the other approach is to use HTTP outcalls to make calls to RPC providers to ask them for the current state of, for example, a smart contract or a balance or whatever, but also to submit signed transactions to those networks. And to make this a bit easier, we have the EVM RPC canister. And if this is something that sounds interesting to you, you should check the two QR codes in the top right corner. They both lead to a workshop and also one part of an Educate series that we did within Code Club. And there, this is covered in a bit more detail. And for signing, as I mentioned already, you need Threshold ECDSA and Threshold Schnorr. With those two, you basically cover all relevant blockchains that are out there. And then, of course, you need a smart contract, a Canister smart contract that builds on top of those two key building blocks, so that uses the Bitcoin integration and that uses threshold signatures or chain key signatures. Okay, maybe again, so what actually is the direct Bitcoin integration? In one sentence, the Bitcoin integration allows canisters on the Internet computer to receive, to hold, and to send Bitcoin, and all of that directly with transactions on the Bitcoin network. That's a cool thing. And to understand why this is awesome, we first have to take a look at how things used to work before this kind of technology was available. So let's think about how assets from other chains were usually made available on a target chain. And a good example here, as we are talking about Bitcoin, are wrapped Bitcoin on Ethereum, so WBTC. So when you are using wrapped Bitcoin on Ethereum, you're actually trusting two groups of people, the custodians and the merchants. So the custodians, they hold the assets, or they hold the actual Bitcoin, and the merchants are supposed to be the only ones that are allowed to mint or to burn wrapped BTC on the Ethereum network. And even though the plural of custodian is used, it's actually only one single company that acts as the custodian in the case of wrapped Bitcoin, and that's BitGo. So to mint wrapped BTC and thus to bridge Bitcoin to Ethereum, first a merchant has to send Bitcoin to the custodian, and then upon receival, the custodian mints the same amount of wrapped BTC to the merchant. So if you as a user want to bring your Bitcoin to Ethereum, so you want to bridge your Bitcoin to wrapped BTC, you actually have to go through KYC and AML with the merchant. Then you need to send the merchant the Bitcoin, and then you need to wait to receive back the wrapped Bitcoin from the merchant. And the other way around, if you want to get back your Bitcoin and get rid of your wrapped BTC, you again have to send the wrapped BTC to the merchant together with KYC and AML, and then you need to wait until you receive back the Bitcoin. So not ideal. And within the wrapped BTC white paper, it's actually stated that you have to trust the custodian not to run away with your funds, not to get hacked, and also to honor the one-to-one backing of wrapped BTC with Bitcoin. And they say to minimize the trust, the custodian cannot mint tokens on their own, but they actually need to initiate the minting together with a merchant. But I guess it should be fairly easy to find a merchant to collude with to print money out of thin air if they wanted to. What they also said in the white paper is that their framework minimizes trust as the credibility of the parties involved is at stake. But to me personally, this is not really a good argument. And as we've seen, reputation doesn't give you any security guarantees. Even reputable companies can get compromised or hacked, or might have an employee that turns rogue. So this is not really something that I personally trust my money with. And this setup that we see here is called a trusted bridge. So a trusted bridge depends on a central entity for operation, and it has trust assumptions with respect to the custody of the funds and also the security of the bridge. So the users, in this case, rely on the bridge operator's reputation and also on their goodwill and their OPSEC and so on, and they have to give up the control of their assets. So in the worst case, what could happen is that you would, for example, send your Bitcoin to BitGo. BitGo says, yes, I hold your Bitcoin, no worries. But in reality, they sell your Bitcoin on the market. And when you want to go back from your wrapped BTC to Bitcoin, you realize that they're not there anymore. So not really ideal. Another thing that I mentioned already is also that they could collude and they could basically mint wrapped BTC out of thin air and create value that is not, or tokens that aren't backed by anything, which is also not really nice. So now that we know how things used to work, let's take a look at how things work now with the direct integration with the internet computer, with the Bitcoin network that the internet computer offers now. So as I mentioned earlier, the Bitcoin integration, I'm going to repeat this many times today, the Bitcoin integration allows Canisters on the internet computer to receive, hold, and send Bitcoin, and all of that directly with transactions on the Bitcoin network. And direct in this context means that there are no trust assumptions required other than trust in the correct functioning of the Bitcoin network and in the correct functioning of the internet computer. So in other words, there are no additional parties required, such as a bridge or any other type of intermediary. And this, of course, results in a much cleaner, in a more secure integration. And what this also means is that wrapped Bitcoin from insecure and centralized bridge services, which have been hacked for billions of dollars in the past, I mean, we see this multiple times a year, are no longer needed in DeFi and in the Web3 ecosystem in general. So previously, I gave you some reasons why chain fusion in general is important, and now I'll give you some reasons why the internet computer or the Bitcoin integration in particular is a good thing or is important. And the first one is, of course, that you can use the internet computer as a Bitcoin layer 2, so you have access to programmable Bitcoin on the internet computer, which is very nice. The second one are on-chain Bitcoin wallets. So because canisters on the IC have access to ECDSA signatures, you can hold your Bitcoin in a canister, which also opens some use cases. For example, this multi-chain wallet. Then you could also send your Satoshis, for example, via chat message on the internet computer in a SocialFi application. You could trade Bitcoin, runes, and BRC20 on tokens on decentralized exchanges. I think this is something that wasn't really possible before, because now you do not trade like a wrapped version of Bitcoin, but you actually trade the Bitcoin. So when there's a trade, you could initiate a transaction on the Bitcoin network to settle the trade. So there's no wrapped version of this Bitcoin. And I think, this probably wasn't possible before. Then you could also have lending markets using, for example, ordinals as collateral. We have chain key Bitcoin now, which I'm going to cover later. And you could also have, for example, a smart contract managed BRC20 index fund. This is actually something that someone is building in our ecosystem. So I think that's pretty exciting, things like those, like Bitcoin DeFi, basically. Okay, so it's important. Before we continue, I assume that the audience is kind of familiar with the Bitcoin network, but one thing I wanted to explain in a bit more detail so that everyone is able to understand the rest of the presentation are UTXOs. And as a simple example here, we have two parties, Alice on the left-hand side and Bob on the right-hand side. And Alice wants to transfer Bitcoin to Bob. So she wants to send in total 400,000 Satoshis to Bob. And for that, Alice has to consume 2 UTXOs, or what they are called unspent transaction units. And those two together add up to the 400,000 Satoshis that Bob is going to receive in the end. Let me see if I have a pointer here, actually. Doesn't seem so. Anyways, where was I? Yeah, 400K Satoshis that Bob receives in the end. And for that, she creates a transaction with the 2 UTXOs that we saw on the previous slide, so the 2 blue ones that are under this transaction thing here. And she uses those 2 UTXOs as an input to this transaction. And there's a new UTXO that's supposed to belong to Bob, the green one, that is the output of the transaction. So as you can see on the slide, the 2 inputs to Alice's transaction were actually outputs from previous transactions. And if you want to create a transaction on the Bitcoin network, you have to spend UTXOs. So you have to use UTXOs as inputs to your transaction to create an output that you can then give to someone else. And of course, otherwise all of this wouldn't make any sense. You can only spend UTXOs that you actually own. So every UTXO has a public key associated with it. And you prove your ownership of that UTXO by creating a signature that's associated with the public key attached to the UTXO. And this is this blue ribbon that you kind of see on the bottom right corner of the 2 UTXOs of Alice's transaction. And once this transaction has been submitted to the network, it is hopefully included in a block. And in this block, there's not only one transaction, but many transactions. And once the block has been mined, the block is chained up with other blocks. And those blocks together form what we call blockchain. And this is what you see on the right-hand side. Okay, so with that out of the way, let's continue. So as we see as I said, for chain fusion or for integrating with another network, you need, or with another chain, you need 2 things. You need reading and writing capabilities to the target chain, and also signing capabilities that are compatible with the target chain. And for the first part, for reading and writing, we have the Bitcoin API, and the Bitcoin API is enabled by this protocol level integration of the internet computer with the Bitcoin network. And on a very high level perspective, what this direct Bitcoin integration means is that replicas, so the physical node machines that we saw in the beginning of the presentation that are running in data centers, they do not only run the internet computer protocol, but they also run basically kind of like a Bitcoin node, and that is called the Bitcoin adapter. And those Bitcoin adapters that are run alongside the replicas of a Bitcoin-enabled subnet, they are able to communicate with Bitcoin nodes in the Bitcoin network. So they are part of this peer-to-peer network that Bitcoin forms. And what this does is that it allows Canisters to fetch balances, block headers, UTXOs, and also to send transactions on the Bitcoin network. And for the second part, for the signing, this we've covered already, we have Threshold ECDSA and Threshold Schnorr APIs that we can use to request, for example, public keys, or to create signatures on transactions that we want to submit to the respective target chain. And for those chain key signatures, we developed an entire protocol suite. So it's not only the signatures, it's actually more protocols included. But it is a signing protocol, distributed key generation, public key retrievals, and a number of other things. So let's go from the top to the bottom on the previous slide. So we start with the protocol level integration and the Bitcoin API. So that protocol level integration, as I mentioned, enables us to read and write Bitcoin state through the Bitcoin API. So on this slide, those monofont texts that are have this gray underline, they're actually methods, all of the methods on the Bitcoin API that you can call. And we're going to cover them quickly and see what they do, what they enable. So before we do that, what this protocol level integration does is that the internet computer can obtain Bitcoin blocks directly from the Bitcoin network, and then it can process the transactions that are contained therein. And by being able to get access to the Bitcoin blocks and being able to process the transactions within the blocks, the internet computer can actually maintain the full Bitcoin UTXO set on-chain on the internet computer. And this uses one of the features that I mentioned in the beginning, like one of those capabilities, and that is that on the internet computer, you have access to a lot of storage, because I think the full UTXO set is something like 30 or 60 gigabytes or something. And then if you want to query the UTXO set in an efficient way, this adds additional storage overhead. So you have even more storage that you need. So maybe with like good indexing, you are at, I don't know, like 90 or 100 gigabytes or something. And this is something that you usually wouldn't be able to do on any other chain, because either the storage wouldn't be available at all, so you wouldn't be capable of storing that much, or if it would in theory be available, it in practice wouldn't be available, because it would cost you millions of dollars, probably even more, probably billions of dollars to store this amount of data. Okay, so now we have the full UTXO set on chain. And with this UTXO set, Canisters can now run queries against the UTXO set. And this allows them to know about the held UTXOs, and thus also the balance of any Bitcoin address, of course, including their own addresses. And these are the first two methods on the slide. So Bitcoin get UTXOs gets to the UTXOs for an address, and Bitcoin get balance is a simplified way of quickly getting the balance for an address. Then next, the internet computer or Canisters on the internet computer are able to submit a signed transaction to the Bitcoin blockchain. And when the internet computer does that, or when Canister does that, the nodes within the Bitcoin-enabled subnet, they actually directly transmit the transaction to nodes in the Bitcoin network without any need for an intermediary that might censor them. And that's pretty nice, because that gets your transaction distributed in the network fairly quickly, because every node, every replica in the internet computer that runs this Bitcoin adapter picks a random subset of the nodes in the Bitcoin blockchain. So it gets distributed very nicely. And that is the Bitcoin send transaction endpoint. Then the next one, to make sure that your transaction is actually included in the block, you need to somehow get access to the current transaction fees. And for that, we use the Bitcoin get current fee percentiles. And then last but not least, a very new feature, I think this is live since a week. Now, Canisters can actually also request Bitcoin block headers. And through this, you can, or a Canister can fetch a raw transaction, or a raw transaction can be pushed into a Canister together with a Merkle proof from any untrusted source. And the Canister is now able to verify that the transaction is indeed part of the Bitcoin blockchain. And this is a useful feature for some use cases. Okay, so now we know roughly what the Bitcoin direct integration is. So there are those nodes, and they run this Bitcoin adapter. And on top of this Bitcoin integration, we have this Bitcoin canister that has this full UTXO set. And on top of both of those things, we have this Bitcoin API that gives us those 5 methods that we can use to leverage this technology in our dApps, in our canisters. So now let's go a level deeper and take a look at how this is actually implemented. So as I said, the direct integration consists of 2 components. The first one is this Bitcoin canister that I mentioned a couple of times now already. And the Bitcoin canister lives on a so-called Bitcoin activated subnet. And it is implemented as a regular NS managed WASM canister. So this is the thing in the top right corner of the left white rectangle, like this orange colored thing. It also says Bitcoin canister above. And this Bitcoin canister, or the API, or the methods that this Bitcoin canister offers, they are made accessible to canisters, to developers through the management canister, which is like basically a facade. It doesn't really exist. It's not really a canister, but it makes developing against those methods easier, because it's, for the developer, it seems like they're just calling that a canister to make things simpler. And then the Bitcoin canister holds the on-chain Bitcoin related state, and that is the full UTXO set, outgoing transactions that canisters want to submit to the Bitcoin network, and also the most recent blocks to allow for fork resolution if this is necessary. And then the other component that I also mentioned is the Bitcoin adapter. You see this in the bottom right corner. And this Bitcoin adapter is run on every node in the Bitcoin activated subnet. And it connects the nodes in the subnet to the Bitcoin network, much like a regular Bitcoin node would do. And for this, you can get blocks into the internet computer. So the on-chain UTXO set is managed by the Bitcoin canister and the Bitcoin adapter communicating through the internet computer's protocol stack. This is what the blue arrow is indicating. And the process here starts with the Bitcoin canister requesting successor blocks to the latest block it received from the adapter. The adapter on each replica of the subnet then obtains the blocks, the latest blocks that the Bitcoin canister hasn't seen yet, from the Bitcoin network. And then one of the replicas is the block making replica, so the one that proposes the next block for this round. And this one provides the requested block, the requested blocks, plural, to the canister, and this block then goes through consensus on the internet computer. So this is what makes it basically secure, that not all, you just don't just take a random block, but all nodes in the network agree, okay, this is the next Bitcoin block that we want to ingest into the Bitcoin canister. And once the Bitcoin canister receives this block, what it does is that it extracts the UTXOs from the transactions within the block, and then it updates the UTXO set that it maintains within the replicated state of the subnet. And if a canister wants to send a Bitcoin transaction to the Bitcoin network, it is first submitted to the Bitcoin canister, where it is queued. And then every subnet round, the Bitcoin adapter on each replica obtains the pending transactions from the Bitcoin canister and queues them for being submitted to the Bitcoin network. And as I mentioned earlier, a cool side effect here is that this leads to a very efficient, very quick distribution of a transaction in the Bitcoin network, as every replica of the subnet submits the transactions via multiple connected nodes to the Bitcoin network. All right, so this part was the direct Bitcoin integration. So reading state from and writing state to the left-hand side, basically on this one slide I had, is covered now. And now we go to the right-hand side, and this is about signing, signing transactions. This is needed to be able, for a Canister to be able to hold assets, right? They need access to keys, and if they want to create transactions, they need access to a signature with those keys that they own or maintain. And this is what we call chain key signatures. And chain key signatures consist of a threshold signature scheme where the private key is shared across the replicas of a subnet. And those chain key signatures, they come in two flavors. So we have, as I mentioned, threshold ECDSA and threshold Schnorr signatures. And what I mean by shared across the replicas of a subnet when talking about the private key is that the private key or the secret key is actually split up into so-called secret shares, and each share is stored on a different node of the subnet. And for this, we use subnets with a high replication factor. That means that they have, in comparison, a lot of nodes within them. So in this case, 28 nodes. And what needs to be done to sign a message is that the nodes within this threshold subnet or threshold signature subnet, they need to coordinate to generate the signature in a distributed fashion. And here, at least 1/3 of the nodes is required to jointly create a signature using their respective key shares or secret shares. And through this, Canisters have control over a unique ECDSA and unique Schnorr key pair, and they can request signatures with the corresponding private key to be computed. And from this unique key pair that they have, they can actually derive an unlimited amount of keys. So this means that a single Canister on the Internet computer doesn't only have a single Bitcoin address because it has a single ECDSA key. No, from this ECDSA key, they can derive an unlimited amount of public keys and therefore also an unlimited amount of Bitcoin addresses, which is really, really neat and really, really useful. And again, it's important to remember that the private key never exists in reconstructed form, but only in its secret shared form, even when the subnet is signing a message. And through this technology, as I mentioned a couple of times now, Canisters are able to natively hold Bitcoin, Solana, Ethereum, or any other chain's asset that support ECDSA or Schnorr signatures. And this is basically a majority of the L1s out there. Okay, so here's a quick example of a Canister interacting with a threshold ECDSA or threshold Schnorr subnet. And to request, for example, signatures, there are two methods. So sign with ECDSA and sign with Schnorr. And to get a public key for the Canister or for any Canister, there's ECDSA public key and the Schnorr public key API methods. And those methods, those four, are again exposed through the management Canister. And as you can see, here again, we use this feature of subnets being able to communicate seamlessly because on the left-hand side, the Canister lives on a completely different subnet than the threshold subnet, right? But it's still able to like call a function on that subnet or trigger a computation on its subnet seamlessly without any overhead for the developers. And this would be an example of a full flow for a Canister to send Bitcoin. So what they would first do is they assemble the signature, assemble the transaction, and then they would request a signature on the transaction from the threshold subnet. So this would be the first step. Then they have their signed transaction, and what they then do is that they call, in the case of Bitcoin, the Bitcoin send transaction API method that we saw earlier to send the signed transaction to the Bitcoin network via the Bitcoin Canister. And then the protocol or the network, the Internet Computer Network, takes care of relaying this transaction to the Bitcoin network. And now I mentioned earlier that a canister has access to basically an unlimited amount of key pairs, right? So let's take a look at derivation for ECDSA and Schnorr. So on the left-hand side, we start off with a master key. And this is basically the ECDSA key of the ECDSA-enabled subnet generated with the distributed distributed key generation protocol, tongue twister. And from this master key that basically belongs to the subnet, we can derive canister ECDSA keys. So we call them canister root keys. And we can derive enough keys to give every single canister basically a canister root key. And we do so by kind of like using the canisters principle as an input to derive to this derivation function, so to say. And now we got from the subnets key to the canister root key, and now from the canister root key again, we can derive an unlimited number of ECDSA key. So as you can see, there's basically there are multiple levels of derived keys. So we can start with the canister root key. From the canister root key, we can derive 2 to the power of 32 keys, and for each one of those keys, again we can derive 2 to the power of 32 keys, and again 2 to the power of 32 keys, and so on and so on. So and this goes on basically indefinitely. So you have access to a lot of keys. Yeah, and an input to derive a key from a canister root key basically on the first level could, for example, be a user principal. So a user calls your canister, and your canister could this way only allow the actual owner of the principal that has been calling it access to the derived key, and this way access to, for example, a Bitcoin address. So you could ask the canister that you're acting with your identity, like, hey, what Bitcoin address should I use to send funds to you? And then the canister would give you a unique Bitcoin address that is only for you. And you would send your Bitcoin to this address. And then only you would be able to trigger the canister to, for example, give you the Bitcoin back if you think of a DEX, for example. And this is what this key derivation is good for. And we will see an example of this later on when we talk about ckBTC, and then it should make more sense. Yeah, and this is actually the API that is again exposed through the management canisters interface. So we have 2 methods here. We have the ECDSA public key method, and we on the left-hand side, on the right-hand side, the sign with ECDSA method. And as the name already suggests, the left method derives an ECDSA key based on the canister ID and the derivation path. We now know what this derivation path is. And what you get back is a ECDSA public key. I'm not going to go through the details. You can take a look at this after the presentation or scan the QR code to learn more. And the right-hand side, as the name already suggests, allows you to sign the signature, create a signature or compute a signature on a message that is represented through a hash, basically. And here you can see that the canister ID is not an input argument, because otherwise I could just pretend to be a different canister and create signatures with that canister's private keys, and that would be bad, right? So for the public key, it doesn't really matter. It's okay to know what public keys and what Bitcoin addresses a canister has access to, but it's not okay to be able to sign on behalf of a canister. So when you call the sign with ECDSA method, the canister ID or the caller ID, so to say, is being derived automatically and used to kind of like gate access to the keys that you can create signatures with. And again, here I'm not going to go into much detail on what the arguments here is, but what you get as a return value is the actual signature. And this is basically almost the exact same thing with Schnorr. So again, you can ask for a public key, you can create signatures. And the only difference here maybe is that in the case of Schnorr, you don't provide a hash of the data you want to sign. You actually provide the data and not a hash of the data. So you provide the message, not the hash of the message that you want to make it signed. And yeah, if you want to learn more about those two functions or 4 functions, make sure to scan the QR code. There's more information available. So now that we have everything we need, let's look at the flow of a Canister sending funds from one of its Bitcoin addresses somewhere else. So as we know, both the ckBTC and the Bitcoin API methods are available for the management canisters. This is why we call the management canister. And the first step that we have to follow through is that we query the Bitcoin canister for the balance of our own address. And this is where this Bitcoin get balance comes into play. Now we know, oh yeah, I have, I don't know, 1 Bitcoin in that address. That's good. That's enough to, for example, pay for the transaction fee and enough to pay my debt or to send the amount that I wanted to send. The next step then is that we request the UTXOs of that address. And the reason for that is that we need a UTXO, as we learned earlier, as an input to our transaction. So now we have the UTXOs. Before we actually assemble the transaction or create a transaction and sign it, we want to find out like what is the current fee for a transaction. So we call it Bitcoin get current fee percentiles method. And from that, we derive the fee that we are setting for our transaction. And once we've done that, we can then go ahead and sign every single UTXO with a call to the sign with ECDSA or sign with Schnorr management canister methods. And then once we have all the signatures, we use the Bitcoin send transaction method to actually send the signed Bitcoin transaction to the Bitcoin network. And then it gets into the transaction pool, into a block, it gets mined. And after 6 confirmations or whatever your threshold is, the funds arrive at the recipient's wallet or address. Okay. So I mentioned a bit earlier, ckBTC, right? So as a bit of a motivation. So because this API methods that we just saw that expose the Bitcoin canister and Threshold DCDSA and Threshold Schnorr, because they're a bit low level, and also because if you do transactions on the Bitcoin network, those transactions are expensive and they are slow. Most of the time when people build projects on the internet computer that leverage Bitcoin as, so to say, a currency or as a value, they will most likely use chain key Bitcoin. So that's kind of like the motivation. And chain key Bitcoin is a synthetic Bitcoin twin token on the internet computer that has much stronger underlying trust and a much stronger underlying trust model than currently existing wrapped or bridged Bitcoin versions, because of its decentralized architecture and because it has been built on top of chain fusion instead of a centralized bridge or anything. So ckBTC does not have any intermediary, anything centralized to work. And that's very cool about it. It makes it very secure. And yeah, we're going to talk about how it works in detail over the next 10 minutes. So like I said, ckBTC is easier to integrate because instead of using those low-level Bitcoin integration API methods, you as a developer can simply access or interact with the ckBTC ledger like with any other ICRC2 ledger on the internet computer. So ICRC2 is basically the equivalent of ERC20 on Ethereum, so it's a token standard. And additionally, ckBTC, opposed to Bitcoin on the Bitcoin network, can be transferred with a very low finality time. So within 1 to 2 seconds, your transaction is finalized. And also, for a fraction of the cost it would cost on the Bitcoin network to send those funds. So on the internet computer, for every Bitcoin transfer, you pay 10 Satoshis. So it's very, very, very cheap. And that makes it very attractive. And using this, let's say, ckBTC scheme, the only transactions that happen on the Bitcoin network are basically to get into ckBTC, you need a Bitcoin transaction on the Bitcoin network. And if you want to get out of ckBTC and you want your raw Bitcoin back, then another transaction is needed. But all the other transfers, they are done with lightning speed and low cost directly on the internet computer. And that's pretty nice. And as you can see in this architecture, there are a number of different components involved. And the first one is the ckBTC minter, that's in the top left corner. And this is a canister that actually holds the Bitcoin on the Bitcoin network, and it mints and burns ckBTC on the ckBTC ledger accordingly. So when you send a Bitcoin, it will mint you ckBTC, and if you send it ckBTC, it will give you Bitcoin back. Then we have the ckBTC ledger, and that is the ledger used on the internet computer network to record the balances of holders and facilitate basically transactions. So it's a ledger. Then we have the Bitcoin canister. We talked about that one already. This is used by the ckBTC minter to get UTXOs and also to send signed Bitcoin transactions. Then there's a KYT canister. This is used to make sure the canister only has clean UTXOs and interacts with clean addresses. And then one thing that's not shown here is the management canister that's used to sign the Bitcoin transactions that are necessary with ECDSA, threshold ECDSA signatures. So now that we have a better understanding of what ckBTC is and what components are involved there, let's see how it actually works by looking at the process of converting Bitcoin into ckBTC. And the process starts by us, the user that wants to convert Bitcoin to ckBTC, querying the ckBTC minter for the address that we should use to send our funds to. And we use the getBTC address. We provide a owner and a sub account, which is basically a principal and a sub account. It's like an identity. And for every pair of owner and sub account, the ckBTC minter gives us a different address on the Bitcoin network. So those addresses that you receive back, they are unique and they are based on the principal and the sub account, and those addresses are controlled by the ckBTC minter. So now I have an address on the Bitcoin network that I know I need to send my funds to. And this is what I do. I initiate a transfer, I create a transaction that sends amount X of Bitcoin to this address. And once that's confirmed, I then have to inform the ckBTC minter about that. I basically have to tell it, hey, I sent you my Bitcoin. Please give me my ckBTC in return. And to do so, we call the update balance method. Here again, we provide the same owner and the same sub account that we provided earlier. And then the ckBTC minter basically calls the Bitcoin canister and says, for this Bitcoin address, do you have any UTXOs, any new UTXOs for me? And so you basically get back all the UTXOs that belong to this address, but the ckBTC minter does some filtering. So it filters out the UTXOs it has never seen before, does a KYT for them. This is not shown here, and then mints the same amount of ckBTC minus the KYT fee into the account of the user. And the account is basically derived from this owner sub account pair that the user provided when he called the getBTC address. And the reason we have to do some filtering is that if you imagine that you send a Bitcoin transaction with 1 Bitcoin to this address that you received by calling getBTC address, and you call update balance, and the minter mints you the ckBTC, and then you call update balance again, the minter would get back the same UTXOs, and it would mint ckBTC again. That would be bad, right? Because then you wouldn't have this one-to-one backing of Bitcoin and ckBTC. So that's why the ckBTC minter keeps track of the UTXOs it has already seen for this particular address, and it has already minted ckBTC for. And yeah, then basically upon seeing new UTXOs, the ckBTC minter initiates a transfer on the ckBTC ledger, and the transfer is basically a minting call. So this way, fresh ckBTC are created and transferred to you, to your internet identity, internet computer address or account, so to say. Okay, now the other way around, ckBTC to Bitcoin. And this flow is based on the ICRC2 standard. And it requires the user to, this is basically a transfer approval flow that you are probably used to from Ethereum if you are not too familiar with the IC. And this requires the user to first set an allowance for the ckBTC minter to withdraw the desired amount of tokens from a user-controlled account by calling the ICRC2 approve method on the ckBTC ledger. So we basically tell the ckBTC ledger, hey, it's okay for the ckBTC minter to, on my behalf, transfer this amount of ckBTC. And then, subsequently, we call the retrieve Bitcoin with approval endpoint to inform the ckBTC minter about our withdrawal intent. So we basically tell the ckBTC minter, hey, I just give you the approval to transfer X amount of ckBTC on my behalf. And in addition to specifying the withdrawal amount, the Bitcoin address where the funds are supposed to be sent on the Bitcoin network must be specified as well. So we also have to tell the ckBTC minter, if you burn a ckBTC and you send out the Bitcoin, please send them to this address. And then next, you see this ICRC2 transfer. This is basically the burn event. So the ckBTC minter burns the ckBTC tokens and releases the Bitcoin on the Bitcoin network by initiating a transaction on the Bitcoin network. And this intent that you want your Bitcoin back is called a retrieval request. And all of the retrieval requests that the ckBTC minter receives by different people, they basically put in a queue. And using a timer, the minter creates a single Bitcoin transaction. So it waits a little bit. It doesn't immediately trigger the transfer on the Bitcoin network. It waits until it basically has a bit more retrieval requests. So the whole process becomes a bit more economic. And this way it can serve up to 100 retrieval requests. And what it does then is it selects UTXOs from the UTXOs it controls with a total sum of at least the sum of the retrieval requests, of course. And then it constructs a transaction with the selected UTXOs as input and one output for each of the retrieval requests. So yeah, basically, if there are two people that want to convert ckBTC into BTC, there would be two or maybe even three. In the best case, if it's a perfect fit from the input to the output, so you have maybe two UTXOs with 100 Satoshis, and both people wanted to withdraw 100 Satoshis, then it would work out fine. But usually, probably there's a bit of, let's say, change. So you throw in maybe one UTXO, and you have two UTXOs as an output, and then a third UTXO for change that you basically give back to yourself or send back to yourself. And as we learned already, every single UTXO has to be signed using the Threshold ECDSA. This is what you see in the bottom right corner, signed with ECDSA. And then once the transaction has been signed, we send it to the network using the Bitcoin API. Et voila, that's it. So 55 minutes. We're basically on time, I see. So yeah, we started a bit later. Here are a number of useful links. So the first one is the Hackathon cheat sheet. This is basically a collection of all the things you need if you're a developer and if you're interested in building on the internet computer. I really, really recommend you to bookmark this and to read through it. There are a lot of nice things in there. Second one is our developer forum. If you have questions, this is the place to be and ask them. The third one are the Bitcoin docs. So everything I talked about right now is basically in the documentation as well. Then this Chain Fusion series that I mentioned that we did with Encode Club earlier, and this one focuses a bit more on Ethereum, but it's still very nice to watch, and I would definitely recommend you to give it a try. Then developer grants. We have a developer grants program. So if you're a developer and you're seeking for some financial aid to pursue your project of dreams, feel free to apply. Second last one is ICP Demystified. If you had a feeling like you were missing some of the foundations, this is definitely a very, very good playlist that we again did with Encode Club. So I would recommend you to maybe watch this one first because it gives you all the basics, and then you can dive into Chain Fusion, Bitcoin, and all the other topics. And then the last one, if you're an Ethereum developer, read this article because it kind of like bridges the gaps from the EVM world to the ICP world and makes it a lot easier to get yourself familiarized with the IC. And yeah, with that, let me, maybe if we have some, maybe 4 or 5 more minutes, let me quickly go through the chat.
There's a couple of questions in the chat, none in the questions tab.
How can we write Solana smart contracts? From Wahid. Yeah, the Solana smart contract, you would need to write in Rust, I think. I'm not too familiar with programming for Solana. If you mean how can we write smart contracts that interact with Solana, this is work in progress. So with the Schnorr, Threshold Schnorr being available, we also have access to EDDSA. And this is a signature scheme that Solana uses for signing transactions for their network. So in theory, it's possible already, but it's just that no one implemented it yet. So I think people are working on something like the EVM RPC Canister, but for Solana. And this would enable you to basically read state from Solana and write state to Solana. But as far as I know, this is not available in production yet. But what we have is GSOL, which is basically like a synthetic version of Solana on the internet computer. So this is basically like ckBTC, but with Solana, and it uses a bit of a different approach to achieve that. Okay, so Ahmed asked, the Bitcoin canister can submit Bitcoin transactions, right? So when it's submitting transactions on a Bitcoin subnet, all of the nodes in that subnet also submit a transaction, right? Both of this is correct, yes. And then he continues, so there will be same multiple transaction submissions depending on the numbers of node in a subnet. Therefore, how I see is managing this situation. I'm not entirely sure what you mean by that, but in general, having the same transaction submitted to the network multiple times in the case of Bitcoin, I think is not a problem, actually. I'm not sure if there's some sort of, let's say, mempool as for Ethereum, where I guess nodes would remove or would not add a duplicate transaction to. But I think in general, the transactions are basically, or make their way through the network on a peer-to-peer basis. So one Bitcoin node sends it to the other peers it knows, and then they send it to the other peers, and that way it basically spreads through the network until everyone is aware of this transaction. And then the next person that is able to create a block includes that transaction if it wants to in a block. So I don't think that's an issue. I think it's actually, like I mentioned in the presentation, a benefit that you have a very nice distribution of your transaction on the Bitcoin network. And you're not at the mercy of a single intermediary that might censor you and say, like, you know what, this transaction I'm not sending out. That would be bad. This is not the case with the Bitcoin canister or the Bitcoin adapter or Bitcoin integration. Why ckBTC minter have to create different BTC addresses depending on the provided account? Why it's not using single address to receive Bitcoin in the ckBTC minting progress? That's a good question. I assume because otherwise bookkeeping would be a bit difficult. If you have basically 50 different people all sending Bitcoin to a single address and all telling the ckBTC minter, hey, mint me that account, that amount or this amount of ckBTC, then I think it's probably not possible for the ckBTC minter without some additional infrastructure to be aware basically which address has the authority or which identity on the internet computer or account on the internet computer has the authority to request the mint of what amount of ckBTC. So this is why the Bitcoin address is derived from the account. And then later on, when you basically call this update, let me go back maybe. later on, when you call this update balance method, the ckBTC minter from this owner and sub account gets the Bitcoin address, it checks the UTXOs, and then it sends whatever amount of Bitcoin it has in this, or whatever new amount of Bitcoin it has in this Bitcoin address to the owner, basically, of that sub account. And that makes, like, it's a separation of concerns, and I think it's also necessary from an operational point of view. And then Ildefons asks, if I send some Bitcoin from my Canister, how do I confirm my transaction is added in a Bitcoin block? And how do I know the number of confirmations of my Bitcoin transaction? Is this the motivation of the new get blocks API? I think you don't, it could be a motivation, yes. You could have someone submit the transaction with a Merkle proof, and you, as the Canister, would get the block header and verify that the transaction indeed has been included in this block. So yes, this is a way to verify this. Other than that, I think you don't really know. I think what you can do is maybe, depending on your use case, maybe check the balance or the UTXOs for the address that you've been sending UTXOs to. Maybe this is in some way giving you an idea whether or not the transaction has been included in a block and mined. And I think with regards to the number of confirmations, I think this is actually built into the Bitcoin integration already. So I think a block is only basically passed from the Bitcoin adapter into the Bitcoin canister if there has been enough proof of work on this specific block, and if the chance of a reorg is very, very low. So I don't know the exact amount of confirmations, but we can go to the wiki page. I don't know if this actually opens a new, no, it doesn't. Let's see. Yeah, it's a bit, it seems like there's some sort of algorithm in place that determines when blocks are ingressed into the IC. So I cannot give you a number now. Yeah, but if you're interested, I'm going to send a link in the chat, and then maybe you can read up on that. And if not, feel free to ask it in the forum. More than happy to get someone to answer it for you. Okay, I think that's it. No more questions, it seems. Thank you, everyone, for participating.
Yeah. Thank you, Moritz, as well, for the amazing presentation, and everyone for participating and for the lovely questions. Tune back in next week for the next presentation starting on Tuesday, I believe, for the next workshop of this series. And all recordings are available on YouTube.
Yeah, you should, like I said, definitely check out the prior Educate series within Code Club, because there's a lot of information in there, and the internet computer is new and it's also complex. So it's, I would say, not that easy to understand if you're coming from an EVM background or from a non-blockchain background. But I think with those Educate series, even though it takes a bit of time to go through them, I think the information in there is prepared in a very nice way. And yeah, it makes it fun to actually learn about the IC. And there are also some workshops, some practical sessions where you learn a bit of coding. So definitely 10 out of 10 would recommend anyone.
Great. Amazing. Okay. Thank you, everyone. And see you next week.